Okay, sometimes I'm brought a problem by a student in organic chemistry, and I'll explain that problem to a student, and the student is surprised, one, at the thought process that goes to solving the problem, and then the expectation that students are supposed to be able to do that. So I want to use an example that a student brought to me recently involving acid catalyzed hydration of different alkenes as an example of how we expect students to think when they are working through different kinds of problems. So here's the problem that the student brought me, and this came directly from their homework. So they were given these structures, right? So 2-methyl, 1-butene, 2-methyl, 1,3-pentadiene. Let's see. 1,4-dichloro, 2-butene, and 2-butene. Okay, so those were our starting materials. And the question seemed to be straightforward, right? Which of these would react fastest under conditions favoring acid catalyzed hydration? And that's all that was given. And so students tend to look at this and think it's supposed to be like a multiple choice question. They should just look and be able to pick. And that's not the way these problems work. And so I want to show you the thought process that it takes to work through a typical question like this. So the first thing I always do is expand my structures so that I can see everything that's there. Sometimes it's difficult for me, and I've been teaching organic chemistry now for most of 28 years. I think I've missed it a couple of years over the course of that 28 years. So I've done this a number of times, and still, skeletal diagrams sometimes can hide things, right? We look at this, and we miss sometimes the 2 hydrogens there. We forget that there's not a hydrogen on that carbon, right? And so expanding the structures gives us a clearer view of what we're looking at in each case. So if you're confused with your skeletal diagrams, don't be afraid to expand the structures. That always helps. So now we have to think about what they mean here by our acid catalyzed hydration, right? Let's think about the specifics of that reaction. Okay, so if we think about our reaction being formed, sometimes we can do this in our heads, sometimes we have to write it out. But if we look at this, the elements of the acid catalyzed hydration, right? The hydronium ion, right? If we've got an acid in water, our strongest available acid is the hydronium ion. So the hydronium ion is acting as the acid. The alkene is acting as the base. We protonate our alkene, making a carbocation. Then our water acts as a nucleophile to attack that carbocation, leaving an alkyl oxonium ion intermediate, right? Our oxygen is still protonated, but another molecule of water can come in, acting as base, deprotonate our alkyl oxonium, leaving behind an alcohol that regenerates a hydronium ion, making the hydronium ion a true catalyst, right? We start with a hydronium ion, and we end up with a hydronium ion. Okay, so when we think about that, and now we think about the other features of this. So one feature of this is that this acid catalyzed hydration is part of the family of reactions called electrophilic additions. So we have to think about what features are characteristic of electrophilic additions. And one of the things that is a feature of an electrophilic addition is that their regiochemistry is driven by the rule of our second favorite dead Russian chemist, that is Markovnikov. And so we have to think about the implications of Markovnikov's rule. And so when we're thinking about Markovnikov's rule, well, Markovnikov didn't know about carbocations. We know that Markovnikov's rule is driven by carbocation stability. And carbocation stability then also affects the rate of the reaction. Okay? If we think about it, we remember, right? When we generate our carbocation, right? If this is where our reactant is, our alkene, if this is energy, and this is reaction progress, then our carbocation is up here, right? And if we remember the Hammond postulate, the Hammond postulate says that the transition state looks most like the thing that it is closest in energy to. And so our transition state, according to the Hammond postulate, is going to look a lot like our carbocation. So things that stabilize our carbocation will probably also stabilize our transition state. And so anything that stabilizes the carbocation and lowers its energy will probably stabilize the transition state and lower its energy for the same reasons. And we know that the activation energy is primarily responsible for determining the rate. If we lower the energy to the transition state, we lower the activation energy, and that tends to lead to faster reactions. Okay? So all of those things have to go into our thinking about our carbocation stability. And so the first thing we need to consider is, what do our carbocations look like for each starting material? Okay? So thinking through the implications of our reaction and what controls the rates of our reaction leads us to know that the carbocation intermediates are what is ultimately going to determine the rate of our reactions, or the relative rates. So, now that we know that, let's go back to our starting materials. So if we have these starting materials, right, and we think about the protonation. So, right, our alkene acting as base takes the hydrogen ion, right? Electrons flow back to the water. Our alkene acting as base takes hydrogen ion, electrons flow back to the water. Alkene acting as base takes the hydrogen ion, electrons flow back to water. Alkene acting as base, takes the hydrogen ion, electrons flow back to the water. And so the question is, what do these look like if we draw them out? So you should draw them out. If you're unsure, draw them. So let's see. We're going to have our new hydrogen on the primary carbon to create a tertiary carbocation there. Here, we're going to protonate the end carbon. See if I can draw this without getting in too big a mess. We'll create a tertiary carbocation there, but our tertiary carbocation is going to be adjacent to that double bond and a CH3 there. Here, our double bond is symmetrical, and so it doesn't matter, but the way I've drawn it, I'm going to put my Cl there, CH2 there, and put my hydrogen there. We broke that. That's going to be a secondary carbocation. And we get that secondary carbocation with a halogen nearby. And then for this one, again, we're symmetrical, so it doesn't matter, but I chose right, so we get a secondary carbocation. Right there. Okay? So we draw out our carbocations. And so in our carbocation intermediates, we've got a tertiary one. We've got a tertiary one, but it is close to that double bond. So it is tertiary plus allylic. We have a secondary one, and we have another secondary one. Okay? So they want us to be able to rank all four of these. So what else do we have to consider? So let's go to the next slide where I've got these drawn a little more neatly. Okay, so here's the carbocations drawn neatly. So let's consider the factors that we consider that stabilize or affect the stability of carbocations. Okay, so what are the things that affect the stability of carbocations? Okay, one of the things that affects the stability is resonance. So, are any of these carbocations stabilized by resonance? So if we make this A, B, C, and D, are any of those stabilized by resonance? Well, again, let's go through our characterizations. We said this one was tertiary. This one was tertiary plus allylic. This one was secondary. And this one was also secondary. Okay? Well, if we look here, and this goes back to the exercises that we were doing that on the tests, right? We see this and we go, oh, this pair of electrons could shift over there because all three of those carbons are sp2 hybridized, and that would move the positive charge from here to here. So there is some resonance stabilizing B. The chlorine is separated, so even though there are unshared pairs of electrons on this chlorine, even though there are unshared pairs of electrons on this chlorine, the charge is separated by this sp3 hybridized atom, and so these electrons can't be shared in a resonance with that carbocation. So the only one that can be stabilized by resonance is this one. So B is stabilized by resonance. Okay? Well, the next thing we consider that stabilizes carbocations is substitution. Right? Substitutions tend to donate electron density. And so if we look at this, right, here we have 3 alkyl groups that can donate electron density. Here we have 1, 2, 3, plus our allylic resonance. Here we have the potential for 1, 2, but we have to think about it. And here we have the potential for 1, 2. Okay? So our substitutions can be, can affect stability. One way is by hyperconjugation. Right? But in each case, there are sp3 sigma bond orbitals that can overlap with the pz of the carbocation. So hyperconjugation could potentially stabilize all of these carbocations, more in the tertiary than in the secondary, but hyperconjugation could be a factor. The other factor we have to consider is the inductive effect. What inductive effects are we going to have? Well, again, if we look, alkyl groups tend to donate electron density through the bond by the inductive effect. But what makes one of these different is the presence of the electronegative chlorines. Because electronegative chlorines tend to draw electrons away by the inductive effect. And because they draw electrons away, this carbon can't be as effective at donating electrons right there. So we have to think about the inductive effect, and the electronegativity of these chlorines affects the ability of this carbon to stabilize the carbocation through the inductive effect. It's losing electron density to the chlorine, so it doesn't have as much electron density to donate to the carbocation. So that suggests to us that even though both of these carbocations are secondary, that the presence of the chlorine makes this carbon less effective at stabilizing this carbocation than this carbon is at stabilizing this carbocation. So if we go through this then, if we go from most reactive to least reactive, and that is driven by most stable carbocation to least stable carbocation, then our most stable carbocation is going to be the one that is stabilized both by resonance and substitution. So our most reactive should be B. Our least reactive should be the one that is stabilized. We've only got substitution is only 2, as is this one, but the effect is diminished by the presence of this electronegative chlorine. And so our least reactive is going to be C. And now if we're going to rank these two, we're comparing a tertiary carbocation to a secondary, and so our next most reactive one is going to be the tertiary one, A, and our third most reactive is the secondary, whose stabilizing effects are not compromised by a nearby electronegative group. And so this is how we would rank these. And that's the final answer. So if you think about what it took to get to this answer, this is sort of the progression ideas we went through, right? So in order to solve this problem, we started out writing expanded structures from skeletal structures so that we got a good look at all the things we're talking about. We weren't missing any hydrogens because we were making incorrect assumption from our skeletal structures. We had to think about the mechanism of the reaction being described, in this case an acid catalyzed hydration, and consider the specifics of that reaction. It is part of our family of electrophilic addition to alkenes. As part of that family, it is subject to being driven by Markovnikov's rule. That is, carbocation stability is important in determining the progress of reactions. When we're considering carbocation stability, we have to consider resonance of the carbocations, we have to consider substitution of the carbocations, and thereby we have to consider hyperconjugation and the inductive effect, and with the inductive effect, the effect of electronegativity. We have to think about all of these processes all the way through in order to get to the answer to the problem. This is what it takes. You're not supposed to be able to look at these problems and immediately solve them. You should have to go through this process on most of the problems. One of the disconnects, I think, between faculty and students is we do expect you to be able to think like this, and as students, you don't think you should have to. But this is what it takes to do organic chemistry. This is the application of, the serial application of multiple principles to break a complex problem down into individual solvable ideas so that you can make a prediction about the outcome. So I hope this helps you in understanding what the expectation is when you see these kinds of complex problems. They are not things you should be able to immediately recall and regurgitate an answer. These are things you need to lay out, think about, write down, and work through the individual steps to come to an answer.